In this video here, we are going to run through some of the key ideas for graphing linear equations as well as linear functions, sort of the tie-in to the two things there. We're going to focus mainly on sections 2, 3, and 4 for this lecture here, and we're only going to focus on the linear equations. Okay, the quadratics and the rationals, etc., are going to be in a later video. Our applications will also come in a later video, so this one here is only to focus on how we take the equations and graph them on the xy plane, as well as taking bits of information to construct an equation to then therefore graph on our xy plane. Normally, when you look at a linear equation, it's given to you in some form such as y equals 4x plus 7. Recall that normally when we work with linear equations, we write it in some form y equals mx plus b. So in our later videos, we're going to see that when you have the equation solved for y, if our variable x there does not have an exponent, notice here that it just says 4 times x. There is no exponent for x. Now that means it's understood that x is to the first power. That's what makes this linear equation here a first degree polynomial equation. So you heard it there. A linear equation is a polynomial equation. It's actually the simplest polynomial equation. We will talk about other polynomial equations such as the second degree polynomial equation, which is a quadratic equation. As you move higher and higher, the third degree is a cubic, and then from there we just call it fourth degree polynomial equations, etc. But the three that we'll focus on there mainly for the polynomials, the first degree polynomial, which is a linear, the second degree polynomial, which is a quadratic, and then the third degree polynomial, which is a cubic. And then from there we'll discuss rational equations, which are those that look like ratios or fractions, radical equations, which have the square root or cubic root, fourth root, fifth root, nth root symbol there. And then also we will have some piecewise functions that we will graph, and we will explore limits with piecewise defined functions at the end of chapter 1. So why did I bring up this linear equation here, y equals 4x plus 7? Because the neat thing here with 1.2 graphs of equations is if we have an equation and we want to graph it, if our equation is linear, the easiest, simplest way to graph a linear equation is to make sure that the equation is solved for the variable y. We do this because typically on the xy plane, we have this independent variable here and we have this dependent variable. We treat the horizontal variable as the independent and we treat the vertical as the dependent. In other words, the value of y is going to depend on the value of x, the way that we have our equation set up. Now we could switch that. We could solve for x and have x depend on y. But the general consensus here is to use x as the independent or the input value and use y as the dependent or output value. So in this case here, what we're going to do is we're just going to plug in any number we want for x. You can choose any arbitrary number you want because remember, what this number line represents is that x can be any number it wants from negative infinity to positive infinity. It can be any value. So, and that with that in mind, choose any number you want for x. So off to the side on your scratch paper or something like that, we can make a little t-chart so that we can assign values for x, plug it in, do the arithmetic, do the multiplying and the addition, right? This here says whatever x is, multiply it by 4, and then add 7. That will give you the value of y. Again, remember, the equation here is establishing a relationship between x and y. What is that relationship? Well, you're going to take x, multiply it by 4, and then add 7. Let's let x be 0, right? 0 is the simplest value. You can plug in 0, and we know that anytime you multiply by 0, that value will always be 0. So if we let x equal 0, let's find out why. 4 times 0 is 0 plus 7. Y must equal 7. We're going to see here that this relationship here, if you have an ordered pair where the x coordinate is 0, well, this ordered pair here is referred to as the y-intercept. Well, what does that mean here? Well, think about it in terms of driving on a vehicle, right? If you pass somebody, you intercept them. Playing football, if you catch the football from the quarterback and you're the defender, you intercept the pass. You are crossing the path of the ball from the receiver to the quarterback, or vice versa from the quarterback to receiver. You got it. So the idea of the y-intercept, this linear equation here is going to produce a line on this xy plane here. Where is this line going to be positioned? Well, what we do know so far is that this ordered pair here is called a solution to this linear equation. In other words, take these coordinates, let x equal 0, let y equal 7, and come over here and plug it back in. 4 times 0 plus 7, this must equal y, which is 7. And we see here that that is the case. So this ordered pair is a solution. Normally with equations, we just get one number that's a solution, but because our equation has two variables, the solution must contain two numbers. That two-numbered solution is an ordered pair. Now, specifically, this ordered pair is special because this is where our graph of the line is going to cross where? The y-axis. So somewhere on this y-axis here, in other words, 0, 7 tells us 7 units up on the axis, we have our y-intercept. Now this is neat here because what we said at the beginning of the video was choose any number for x. I decided to choose 0 out of the infinite choices that I had. I can choose any number as small as I wanted. I could have chosen any number as large as I wanted. I chose 0, it was easy to work with. If I had an infinite number of choices for x, that must mean that I have an infinite number of solutions for this equation. And that would be true. Think about a line. When we draw a line is never ending. If a line is never ending, it's infinite in size. Therefore, the amount of ordered pairs that make up that line, there must be an infinite number of ordered pairs. We'll see that. You can sit here and plug in as many values for x as you want. Conversely, if you want to, you can assign numbers for y and solve for x. But because we have this here solved for y, it just makes it much easier to plug in for x. Again, remember, x is the input value. It's the independent variable. Choose numbers for x, solve for y. Let's try it again here. What happens if x is, let's say, 2? If x is 2, well, let's run through the arithmetic again. If x equals 2, then 4 times 2 plus 7 is 8 plus 7, which is 15. So again, we see that this relationship here, in this equation, this relationship here gives us the ordered pair 2, 15. 4 times 2 plus 7, 15. Ordered pair 2, 15. So again, where do we find the ordered pair 2, 15? Well, 2 is positive, 15 is positive, so we're going to be somewhere over here in quadrant 1. 2 units to the right, and way up here will be 15 units. I'm not sure exactly where that is, so I'm just going to put it somewhere up there very high. Because we're running out of space up here, I want to get a good idea of this graph on the xy plane we have here. So I'm actually going to choose some negative values for x and see what happens there. What happens if x is, let's say, negative 2? Let's let x be negative 2. So here, we'll plug in the negative 2. 4 times negative 2, remember that a positive times a negative is a negative. So 4 times negative 2 is negative 8. What's negative 8 plus 7? Well, remember that that's also the same as 7 minus 8. If you're negative and you add 7, you're going to get larger, but you're still in the negative here. We are negative 1. So when x is negative 2, our output value is negative 1. Well, we get this other ordered pair. Negative 2, negative 1. Let's see where we graph this. Negative 2 says we will move to the left 2 units. The negative 1 says we will move down 1 unit. Now, the neat thing here with geometry is Euclid said way back when that in order to graph a line, we only need 2 points in space. Now we already have 3 points here. So we have more than enough ordered pairs to graph an appropriate line for this equation. Let's go ahead and try that out. I have my handy dandy meter stick here. And what I'm going to do is I'm going to use this straight edge. Now, again, my drawing is not to proportion. So this dot here, I didn't trust in the first place. I'm going to run off of these 2 dots here. Yeah, we'll go with something like that. And so we see here we have the graph of our linear equation, y equals 4x plus 7. So what this tells us here is that any point that lies on this line here, these infinite points, these infinite ordered pairs, these are all solutions to our linear equation, y equals 4x plus 7. In order to check this line, we can continue to plug in values for x. That's fine. There's nothing wrong there. But what I want to do here is I want us to take note of this special ordered pair right here. Now, what do we think that ordered pair is called? If where we cross the y-axis, if that's called the y-intercept, then crossing the x-axis, that special ordered pair is called the x-intercept. Now, for the y-intercept, the x-coordinate is always 0. So in general, for any y-intercept, the x-coordinate is always 0, and then we will have to determine what the y-coordinate is going to be. Here, with our xy chart, finding these ordered pair solutions, we saw that the ordered pair 0, 7 is in fact the y-intercept. Now, what we're going to see in just a moment is we could have found that out by simply looking at our equation. Because it is in this y equals mx plus b form, this value here tells us what the y-intercept of the what the y-coordinate of the y-intercept is going to be. But we'll get to that in just a moment. How do we normally find the x and y intercepts? Well, again, if we said here the y-intercept always has x coordinate 0, then for the x-intercept, the y-coordinate is always 0. Because think about it here. Wherever we cross the x-axis, we haven't moved vertically. That ordered pair right there that sits on the x-axis has not moved vertically. If it has not moved vertically, then its position vertically is going to be at 0. It has not moved up, nor has it moved down, so it can't be a positive or negative number. It just has to be 0. It has not lifted vertically or dropped. Same thing here with the y-intercept. The y-intercept has an x-coordinate of 0 because think about it. If you lie on the y-axis, you have not moved off of the y-axis. If you move off the y-axis, you will either be positive or negative. Because you have not moved, you're going to stay right there. You're going to remain with a coordinate of 0. But how do we find these on a regular basis? Well, it's pretty neat here. In order to find this x-intercept for this graph, we see where it crosses. Graphically, we see where it is. It's on the left side of the origin. Because it's over here, the x-coordinate should be a negative number. That would make sense, right? The x-coordinate says if you move this direction, you have a positive x-coordinate value. But if you move this direction, you're negative. So all of these ordered pairs over here to the left of the y-axis have negative x-coordinate values. So it makes sense that this x-coordinate is negative. But what is it and how do we find it? For every x-intercept, the y-coordinate is 0. So what we can do here is actually take this 0 and plug it in for y, and then solve for x. We'll go back to our old linear equation ways of solving for the variable x. Set y equal to 0. Let's do that right here. Setting y equal to 0, we have 0 equals 4x plus 7. 0 equals 4x plus 7. We want to get x by itself. X was multiplied by 4, and then we added the 7 to it. to reverse these steps to get x by itself, because we want to solve for x, what was the last thing we did? We added 7. So let's subtract 7. That'll get rid of that adding of 7. If we subtract 7 on one side, recall that this chemistry vibe, we want to balance the equation. We want to balance it on each side of the equation. So here's our equation. Subtract 7 on the right side. Let's subtract 7 on the left side. 0 minus 7 is negative 7. 4x plus 7 minus 7 is simply 4x. Last thing here we need to do, because we were multiplying the x by 4, let's do the reverse of that. Let's do the inverse of that and divide by 4. So what does x equal here? X equals negative 7 over 4. Now the good thing here is because we're dividing by 4, we can understand that as quarters. So this is negative 1 3/4, negative 1.75. We can write it as negative 1.75. Anytime you have a fraction, if you divide that in your calculator and you get a very, very nice terminating decimal, I encourage you to write that. However, if you had a fraction such as 1/3, we know that putting 1 divided by 3 in the calculator is going to give us a repeating decimal. Instead of having that repeated decimal where you round off, the round off gives you an error, just leave it as a fraction. A fraction like this, there's no round off. That is the exact value of this fraction. But writing 1/3 as 0.33, we know that's really not the value of 1/3. It's actually 0.3 repeating. So if you want to get away with writing that, I guess that's okay. It's normally just easier to leave it as a fraction. So I would highly encourage that. So we found this negative value here. Where does it cross the x-axis? It crosses at negative 7 over 4, which is negative 1.75. This ordered pair here, this is our x-intercept. So what you're going to see here is that when you're given a linear equation, if it's already given to you and you're being told to graph it, all we really need to do here is just find some ordered pairs that are solutions to this equation. How do we do that? Solve for the variable y, and once you solve for the variable y, just start plugging numbers in for x. When you plug numbers in for x, do the arithmetic, get a y value for your ordered pair, and you will have found an ordered pair solution. Graphing those ordered pairs and then drawing the line through it. Again, right here we saw this ordered pair was a little off because my drawing's off by the scale. But we see that any ordered pair, as we extend this line as far as we want to, we can plug in x equals 100, 1,000, 1,000,000. We can plug in x equals negative 100, negative 1,000. It doesn't matter, right? Because negative 100 times 4, negative 400 plus 7, negative 393. So you would have this ordered pair way down at the bottom. So that's pretty fun. What we're going to see moving forward with functions is when you solve for y, we are going to switch the notation, and instead of writing y equals 4x plus 7, we will write f of x equals 4x plus 7. That's why it's so important to write it in y equals mx plus b form, otherwise known as slope-intercept form. Because the idea here is to work with functions, to graph functions and interpret functions and predict something that's going to happen later on. So linear equations, this is our first step. Let's go ahead and take a look at one more example as we make our discussion. So as I said before, as Euclid said before, in order to graph a line, you only need to find 2 ordered pairs that satisfy that equation, that linear equation, and then you can draw your straight line through those 2 ordered pairs. As we saw right there, you may or may not think this, but I'm one to think so. The 2 easiest ordered pairs to find for any linear equation are the x and y intercepts. Because why? The x-intercept always has a y coordinate 0, and plugging in 0 to an equation makes the equation much easier to work with, right? It usually nullifies some sort of term that is in the equation. So let's again think of an example here. 5 minus 3x equals y. If we're being told to, if we're being told to graph this equation here, notice again that it is solved for y. So how would I want to go about graphing it here if I wanted to find ordered pairs to graph this equation? Well, again, think about the x and y intercepts. The x-intercept, this ordered pair here, always has a y-coordinate 0. For the y-intercept, for any linear equation here where the slope isn't undefined, we'll talk about that later, or 0, for the y-intercept, the x-coordinate is always 0. So what is the x-intercept for this linear equation? Let's plug 0 in for y and solve for x. 5 minus 3x is 0. So we want to get x by itself. Notice here 5 minus 3x. What we can do here is we can subtract the 5 and move it over here. Or we can actually add the 3x. And now I'm looking at this as, if you can work with as less negatives as possible, try to go about that. I'm going to add 3x to each side. From here, we have 5 equals 3x. And now because we're multiplying the x by 3, we'll divide off the 3. And we have here that the x-coordinate of our x-intercept is 5/3. Now again, we found that the x-intercept is the ordered pair 5/3, comma 0. Again, if you think, what is the fraction 5/3? It is 1 2/3, approximately 1.67. But once again, we don't want to make that rounding error, so we'll just leave it there as 5/3. That's going to be very important when you do your homework online as well. The computer is very testy. They do not like to make that mistake there, so you do want to leave it as a fraction. Likewise, let's go ahead and find the y-intercept. To find the y-intercept, we'll set x equal to 0. And again, notice how easy it is here to find the y-intercept. When we set x equal to 0, this becomes 5 minus 3 times 0. Well, 3 times 0 is just 0. So we get here that 5 equals y. If 5 equals y, y equals 5. So our y-intercept here is the ordered pair 0, 5. These two ordered pairs satisfy this equation. They are solutions. So if we wanted to graph this linear equation here, we just need to plot these 2 points and draw a line through it. It's as simple as that. You could have gone the other way. You could have sat here and made your t-chart. And again, there's nothing wrong with making a t-chart here. You plug in a couple of numbers. We found that, well, if x is 0, y is 5. What happens if x is 1? Well, if x is 1 here, 5 minus 3 is 2. What happens if x is 2? Well, 3 times 2 is 6. 5 minus 6 is negative 1. Do we see a pattern here? Notice that when x is 0, y is 5. When x is 1, y is 2. When x is 2, y is negative 1. Do we see a pattern with this table here? Can we see a pattern? As x increases by 1, right? As x increases by 1, what are the y values doing here? We'll go a little bit further here, because what we're trying to do is establish a pattern. What happens if x is 3? 3 times 3 is 9. 5 minus 9 is negative 4. Okay, what's the pattern? As x increases by 1, the y's are decreasing by 3. Right? Do we see that there? As x increases by 1, the y's decrease by 3. I wonder why they're decreasing by 3 every single time. When we have the linear equation solved for y, that is in the y equals mx plus b form. That is our slope-intercept form. Where's the x at in the equation? What's in front of it? All right, minus 3x. When you have your linear equation solved for y, and it might be easier to rewrite this. What if we rewrote this and said, okay, y equals negative 3x. This 5 here is positive, so plus 5. Right, we can rewrite. There's nothing wrong there. We switch this around. We wanted to write the y first. If x equals 4, 4 equals x. You can flip that around. There's nothing wrong. Y equals negative 3x plus 5. So if you notice here, what we're going to see in the next video, when you solve your linear equation for y, first thing, you switch the notation to f of x, and what follows here? Negative 3x plus 5. Whatever number is in front of the x here, that's your slope. Slope is a measure that tells us, one, the steepness of our line, right? We remember that word slope that tells us how steep our line is on the graph. But what it tells us is here, how is one variable changing with respect to the other? That's what it means. That's what slope means for us. How is one variable changing with respect to the other variable? We're looking at x and y. Notice that as x changes 1 unit, y is changing by negative 3. Right? It's going down 3. 5 goes to 2, which goes to negative 1, which goes to negative 4. I can guarantee you this next number here would be negative 7, then negative 10. Just plug in 4, 5, etc. You will see that pattern start to be created. And it's because the slope of the line, or the change in the y variable with respect to the x variable, the change in the y variable is negative 3 for every 1 for our x variable. So that's what the slope's telling us, and that's what we're going to see in the next video as well. So to get back to graphing this line here, let's graph the two ordered pairs, 0, 5. So we go up 5 units on the y-axis, and we have our y-intercept. For 5/3 is somewhere between 1 and 2. So here's 1, here's 2. 5/3 is going to be approximately right here. 2 points is all we need to graph our line. So we can go right over here and do our graphing. Again, don't judge me for my artwork too much, but we see here again, we have a line graphed for our linear equation, or what we're going to start calling our linear function. Why are we using the word function? Now, if you think about a function in an everyday process, how does your body function? How does a television function, right? There's a process going on. There's input and output. We have to put in something for a function to be processed and created, and then we're going to get something out of it. For this here, mathematically, what we mean is we're going to plug in a number. A process is going to happen, a function. Well, what is that function? In this case here, we're going to plug in a number. We're going to multiply it by negative 3, and then we're going to add 5. That's the function, right? The equation is a function because something is happening. Something's going on here. What's going on? Mathematically speaking, multiplication is going on and addition. That's what's going on here. So that's the function. Whatever number we generate out of it, whatever that y value is, or whatever that function value is, right? Input, output. You plug in a number, you do the arithmetic, you get a number out of it, hopefully. And with that said, that ordered pair comes from the function. That ordered pair is a solution to the function. Functions are what we're going to use moving forward. All right, everyone, so we're going to look at a few problems here out of the book. Let's take a look. This is on page 19. We're actually going to look at the first 2 problems here. Again, I wanted to keep this at just linear equations and linear functions right now. The next video will deal with quadratics and other polynomials. As you see there, all those problems listed below, 23 through 28 and even 29, although you can't see all of it, we will discuss each of these and how we sort of move forward. If you can already get an idea for problems such as 25 through 28, factoring. A lot of these things that we talked about in college algebra are going to be right at the forefront because all of our algebra studies is essentially what we're working with here when we deal with calculus. Even calculus 1 through 3, a lot of the techniques in algebra such as factoring quadratics and factoring larger polynomials will be sort of the shining light, and it's really kind of all the same here in applied calculus as well. Let's go ahead and look at the first 2 problems. It says here in the directions, and again, I stress more than anything, always look at the directions. They will tell you how to answer the question. If you think you know how to answer a question, but then you realize you didn't read the directions correctly, that's a tough one. I say that because in earlier classes, if you are answering a question and it's telling you to place the variable in the box as you type it out, if you put B in lowercase, but it should be uppercase, it will be picky about that. So I do tell you to stress it more than anything I can to read the directions when you are answering the questions on homework. So it says find the x and y intercepts of the graph of the equation. We're going to go ahead and do that one step further, and we're going to graph it, and then we're going to take a look at solving for the variable y. Number 23, we have 2x minus y minus 3 equals 0. So it's telling us to find the x and y intercepts. Now again, the x-intercept always has y-coordinate 0, and the y-intercept always has x-coordinate 0. So let's go ahead and start with the x-intercept. For the x-intercept, set y equal to 0. This is going to zero out. 2x minus 0. If you subtract 0, you're doing nothing. So here we get 2x minus 3 equals 0. Notice again, it's a nice little one variable linear equation. 2x minus 3 equals 0, so we'll add the 3. Adding the 3 to each side of the equation, 2x equals 3. Now dividing off the 2. Dividing 2 on each side, x equals 3 halves. So again, we find a solution of 3 over 2, but what does that mean? What were we doing in the first place? We're trying to find the x-intercept. The x-intercept for this linear equation. So our x-intercept is an ordered pair. It's always an ordered pair with x-coordinate 3 over 2 and y-coordinate 0. To find the y-intercept, set x equal to 0. Two times 0 is 0. Excuse me. So 0 minus y minus 3 is 0. So 0 minus y is just minus y. A lot of ways that we can interpret this right here. Minus y minus 3 equals 0. I noticed that if this was just a regular y, I would be good. It's minus y. So if we add y to each side, we'll have our solution. Negative y plus y, any number subtract itself, any negative number plus its positive self, that's going to cancel out and give us 0. So this right here is basically 0 minus 3, which is minus 3. On the right-hand side of our equation, 0 plus y, or y plus 0, is simply going to be y. So again, what does this tell us here for our solution of y? Our y-intercept is the ordered pair 0, negative 3. For this linear equation, the only two ordered pairs that I need really are the x and y intercepts. Now I can find as many ordered pairs as I want. Again, make your xy table, plug in numbers for x, solve for y, you're good to go. Go ahead and graph this here. X-intercept, 3 halves 0. Remember, 3 over 2 is 1.5. So 1.5 is directly in between 1 and 2. So our x-intercept is right there between the units 1 and 2. Negative 3, 0, negative 3 tells us we're actually going to drop 3 units. And then drawing our line, we have our graph. Now, I want us to start noticing the shape of our line every time we graph. We've graphed 3 lines so far. Which way are they tilting, right? Are they tilted like this? Are they tilted like this? What does that mean? Why are they different in some cases? Well, I'll tell you this here. Notice that the numbers on the horizontal axis, right, they're smaller over here. Negative 10, negative 5, negative 2. Then we get to 0, 1, 2, 3, etc. So we're moving from left to right. When you read a graph, you want to read it from left to right. What are the y values doing? As we look at this graph from left to right, what are the y values doing? Well, they go from negative 3 to 1/2 or 1.5. They're getting larger, larger, and larger. This line here is an increasing line. When our line is tilted in this direction, notice that we are getting larger. As we look left to right, our y values are increasing. This is an increasing line, which tells us our slope is positive. So when our line is tilted in this direction, we have a positive slope. When our line is tilted in this direction, we have a negative slope. What do we think it means when our line is horizontal? Is there any slope at all? you would say there's no slope. All right, here we have a positive slope, you're walking up the mountain. Here we have a negative slope, you're walking down the mountain. If you were just walking out in the flat plains, is there any slope at all? If you had to give a number to that slope. And then what about a cliff? What about a line that is vertical? Is it even possible to hike something that's vertical? So what numbers, if any, would we give? We'll talk about that in one of our next videos. We have our line graph. This line here, this linear equation, if you had to assign a picture to it, this is that picture. But I want you to think about this in terms of linear functions. If we wanted to write this as a linear function, we must get this equation solved for y. And there's many ways we can go about this here. We can add over the 3, subtract the negative 2x, but then we have that negative in front of the y to deal with. So what I would encourage you to do here is simply add the y to each side of the equation. If you add y to each side here, notice what you get. You have 2x minus 3 equals 0 plus y, which is y. So what is y? Y is, or y equals, 2x minus 3. So again, I encourage you, if you want to, write the y out front. Y equals, what does y equal? It equals 2x minus 3. This is very important for us to do here because now that we have written this equal to y, we can see how y depends on the value of x. What does y equal? Well, it equals whatever x does, multiply by 2, subtract 3. Y depends on what we plug in for x. Y is dependent, therefore we write it as a function of x. That's why we use the f of x notation. It's a function of x because what is a function? It involves plugging in a number and getting out a number according to the arithmetic. So the function occurs when we plug in the x value and we get a function value out of it, which is the y value. So what we're going to write here instead is f of x equals 2x minus 3. So why is this important? This linear equation, 2x minus y minus 3 equals 0, that equation can be represented by a linear function, f of x equals 2x minus 3. What does 2x minus 3 tell us? The slope of our line is 2. Well, what did we say before? Because this graph is increasing, the slope must be positive. Whatever number is in front of the x, when this is equal to y, that's your slope. 2 is a positive number. The slope is 2, it's positive, therefore the line is increasing. The negative 3 tells us the y coordinate of our y-intercept. Negative 3, negative 3. Therefore we graph. Now again, when you have it set equal to y, once you set it equal to y, you can create your t-chart. Had you not already graphed it, now again, that's why we mentioned the x and y intercept are really easy to find, and I would encourage you to use them to graph your function or your equation. But if you go ahead and solve your equation for y, now you can use your t-chart and you can find as many ordered pairs as you want. If you're just interested in understanding what is the pattern, we said our slope is 2. So because our slope is 2, then for each time we increase by 1 over here for x, we should increase over here by 2. Let's try that out. If x is 1, here's the fun thing too, function notation. It's also much easier to evaluate by plugging in. What do we mean by that? If we let x equal 1, function notation lets us write this as f of 1. What is f of 1? F of 1 says we have this function here, but we're going to let the input value be equal to 1. What happens when we take 1 and plug it through the function machine? All right, we're going to take 1, we're going to plug it into the function machine, and we're going to let the function happen. What's the function? We're going to take 1, we're going to multiply it by 2, and we're going to subtract 3 and see what happens. 1 times 2 is 2, minus 3 is negative 1. F of 1 is negative 1. What does that mean? We plugged in 1. That's our input value. That's our x coordinate. Well, what do we get out? What does the function equal? The function equals -1 when x equals +1. So our ordered pair here is 1, comma, -1. What happens when x is 2? What happens when x is 2? Let's plug 2 into the function and see what the function equals when x is 2. 2 times 2 is 4, minus 3 is 1. What about f of 3? F of 3 means we're going to take the number 3 and plug it into the function and see what the function equals when x is 3. 3 times 2 is 6, minus 3 is 3. We can take this one step further. Just to get an idea, f of 4, well, 4 times 2 is 8, minus 3 is 5. Do we see the pattern here? -1, 1, 3, 5, right? They're increasing by 2 every single time the x value increases by 1. That's because the slope here of our function is 2. And just for time's sake, let's go ahead and look at 24 as well. We'll just do the x and y intercepts. 4x minus 3y minus 6. If we want to find the x-intercept, we'll set y equal to 0. Set y equal to 0. And anytime we set y equal to 0, notice the entire term goes away. 3 times 0 is 0. If you subtract 0, it does nothing. So basically, put your hand over the y term. 4x minus 6 equals 0. 4x minus 6 equals 0. We want to get x by itself. Let's add 6 to each side. We're adding 6 because that's the opposite of subtracting 6. Right? If we wanted to subtract 6 again, we'd get minus 12. That's not helping us out by isolating the variable x. Let's add 6 to each side. 4x equals 6, so divide 4 on each side. X equals 6 over 4, right? We have 6 quarters or 6 over 4. But we notice here that the top and bottom number are both even, so extracting a 2 on the top and bottom and then canceling them out, 6 over 4 is the same as 3 halves. So our ordered pair here is 3 halves, comma, 0. Once again, you see 3 over 2 is simply 1.5, directly in between 1 and 2. All right, what's our y-intercept? Y-intercept set x equal to 0. If x is 0, we're going to plug out that entire, we're going to cancel that entire term there. We're left with negative 3y minus 6 equals 0. Want to solve for y, so we'll add the 6. Notice some of this can get very repetitive. It's just kind of beating the drum. Divide negative 3 on each side. What happens, right? 6 divided by negative 3? Negative 2. So we get 2 ordered pairs that satisfy this linear equation. Euclid says that's more than enough to graph our line. So we'll go to our xy plane here. This xy plane shows the relationship between x and y. This relationship here has an infinite number of solutions. We only found 2 of them. Remember, you can find 100 solutions, 1,000,000 solutions just by simply plugging in a value for x, solving for y, create your ordered pair. That's a solution. Graphing 0, negative 2. Graphing 3 halves 0. Right in between 1 and 2, we'll have 3 over 2. Once again here, we see that our line is in fact increasing. So even before we solve for y over here, we understand that this line does have a slope that is positive. And just for giggles here, let's go ahead and solve for y to give us an idea of what the function is we're working with here. Again, in order to see the function of a linear equation, we solve for the variable y. This also puts us in slope-intercept form, which makes it much easier to determine the slope of the line as well as the y-intercept. All right, how do we want to solve for y here? Let's say we don't see it, right? We don't see that we can just move this over and then divide by 3. Let's move everything else. Subtracting 4x is going to cancel, but I have to do it on the left side as well. Again, we want to get y by itself. We have y. It's multiplying -3, and we have -6. So we need to add 6 to both sides. Notice again here that minus 4x plus 6, we cannot combine this, right? You cannot write this as 2. You cannot write this as 2x. They are unlike terms. If you do not recall what a like or unlike term is, just remember that each term, right, those numbers and variables separated by the plus and minus signs, terms have to have the same variable raised to the same exponent. There is no variable attached to the 6. Therefore, we cannot combine through addition or subtraction with this minus 4x. It must stay as it is. So what we have here is minus 3y equals minus 4x plus 6. Now, to get y by itself here, the last thing we need to do is divide by -3. Notice how on the right-hand side, we are dividing all of this by -3. But the way that we're going to write it, it needs to be in mx plus b form. There should only be 2 terms when you have a linear function. And notice before we had something like 4x minus 3, 2x plus 7, etc. We don't need this really large fraction over here. But what we can do, because we are dividing by a real number, we're dividing by -3, we actually can break apart this really large fraction into the sum or difference of 2 smaller fractions. Let's see how we're going to do that. On the left side, we just have the variable y. But on the right-hand side, notice what we have here. It says -4x divided by -3. So we have this negative number up here divided by this negative number in the bottom. A negative divided by a negative is a positive. So now we're left with 4x divided by 3. 4x divided by 3. Well, the neat thing with the division of numbers here is if I have 4x divided by 3, I can actually write that as 4/3 times x. Because notice here with 4/3 times x, this x here is understood to be over 1. So at any time, I can take that x variable and I can toss it in that numerator. But for the sake of understanding what is the slope of this line, it's the number that's out in front of the variable x. If I leave the x up here, we're going to think, oh, the slope is 4, but it's not. It's 4/3. It's 4 divided by 3. So we're going to get a 4/3 as our slope. But what about over here? A positive 6, right? Positive 6 divided by -3. Positive divided by a negative, okay, that's negative. What did we say the y-intercept was? 6 divided by -3 is -2. So this linear equation has a function that can represent it on the graph. It's this function right here. All we have to do now is just rewrite this, not y equals 4/3 x minus 2, but rather f of x equals 4/3 x minus 2. And so what have we been saying this entire time? I can take any number I want and plug it in for x here. Choose any number you want. Choose 10. Well, 10 times 4/3 is 40/3. Subtract 2, you're going to get 34/3. That's a real number to work with. That is a real number that we can graph on this xy plane. There is no number that can't be plugged into a linear function. So here's the note here. This is the big one. The domain of a function, the domain, that's a big word here, especially working with functions. The domain of a function, those are all the numbers that you can plug into a function. So it's all the x values that you can plug into a function such that you get a real number out of it. Well, what do we mean? With this linear function, if you plug in any real number, you are going to get out any real number. You can plug in pi, right? Pi is an irrational number because it's never ending. There is not a repeating sequence. There's no pattern that can be established with pi, that ratio between the circumference and the radius of a circle. It stays irrational. It's non-repeating. There's nothing you can do about it. So you can still plug pi into this, though, because an irrational number times a fraction is an irrational number. Minus 2 is an irrational number. Irrational numbers are real numbers. You can graph them. So there's no, and negative numbers. If I plug a negative and multiply it to a positive, it's negative. If I subtract 2, it's negative. A negative number is a real number. So the domain of a function is any number that you can plug into the function. So it's the x values such that you get a value out of it. For a linear function, and in general, for any polynomial function, the domain of a polynomial function is what we call all real numbers. What do we mean by that? For a polynomial function, you can plug any number into that function that you want to. Well, what do we mean? What real numbers? What did we say here? This number line extends the number line that we work with here, the x-axis, is an infinite number line, infinity, the infinity symbol. But remember that negative numbers can get so small, they can get so minuscule. -5, -10, -1 million, -100 million. There's a never-ending cycle to getting as small as possible. So what we do here is we have to just designate it. Because if you write a number, if you write the smallest number you can think of, I can go in and just subtract 1 from that and say I found one smaller. But then you can subtract another 1 or subtract another 1 million. You will never find the smallest number. So we will designate the smallest number with a symbol. A symbol is not a number that you can plug in. It's just an idea that you will never reach your destination. It's never ending. Same thing with positive infinity. Positive infinity just means you're getting larger and larger. Negative infinity means you're getting smaller and smaller. So what is the domain of a polynomial function? It is an interval of numbers. Remember, a domain is a set of numbers or an interval of numbers from negative infinity to positive infinity. This is the domain of a polynomial function. What this means is you can choose any number you want. It does not matter. Choose any number you want in the infinite realm of numbers. Choose any number you want and plug it into a polynomial function. You will get out a real number. The output is going to be a real number. This will start to break apart when we look at rational functions and radical functions, as well as piecewise functions. That's where this domain idea starts to fall apart, because there might be something called a discontinuity in the graph. There might be a hole in the graph. There might be an asymptote in the graph. And in general, there might just be a large gap due to the piecewise defined function. But for linears, quadratics, cubics, and any polynomial function, you can plug anything you want in. Do the arithmetic, multiply, divide, add, subtract, raise it to the power of 2, or etc. You will get some number out of it. For that, the domain of a polynomial function is any number from negative infinity to positive infinity. We use parentheses. Remember that in interval notation, we use parentheses to indicate that the endpoints, this smallest number, and this largest number are not included when we use parentheses. When those endpoints are included in the solution or in the interval, we use the bracket notation. Right, brackets, for example, if we have this interval here, -3 to +4, where there's a bracket next to the -3 and there's parentheses next to the +4, what does this indicate? This tells us that in this interval, this possible solution, -3 is going to be considered. +4, however, is not considered a solution. That's why we use the parentheses around it. However, any number in between, all of those infinite numbers, right? There's -2, -1, 0, 1, etc. There's also the fractions, right? The 2/3, the -1/2, pi, right? The irrational number pi is also in this interval here. It's every possible, conceivable, infinite number you can think of that would be in the solution. The interval notation using the bracket or parentheses is just giving us an idea about these visible numbers. Do you or do you not include them? That's the question. But any number in between will always be included in the interval notation.